In this video, we're going to talk about salinity, which is defined as the total quantity of dissolved inorganic solids in water. So inorganic in that they're not derived from living organisms, and dissolved in that they're not particulate, they're fully in solution. Ocean waters, as you know, are salty, and they have a salinity between about 32 and 39 grams per kilogram. So that's number of grams of salt per kilograms of water. So 34 grams per kilogram is a fairly typical upper ocean salinity. 34 grams is the weight of 6 quarters, so 6 coins, in every 1 litre of water. So it's a fair amount of salt. Rivers, on the other hand, are almost fresh water with about 0.1 grams per kilogram. The saltiest place on Earth is the Dead Sea. So this is a lake or inland sea that doesn't have any outflow. So the water comes in, the very little salinity that's in there, but it's a high evaporation region in the Middle East, so the water evaporates and we're left with the salts, and over time that's built up to have around 130 grams of salt for every kilogram of water. So why are these salts dissolved in water? Well, water is a very powerful solvent. It's the most powerful of all the natural liquids that dissolve in compounds. And the reason for this is that water is what's known as a polarized molecule. So water is this sort of Mickey Mouse shaped molecule here. We have a large oxygen atom, which has a negative charge, and we have 2 smaller hydrogen atoms that have a positive charge. So we end up with one end that has a negative charge, and then another end opposite that has a net positive charge. So when it encounters salt, in this case sodium chloride is just regular table salt, the negative ends of the water are attracted to the positive sodium ion, and likewise the positive ends of the water, the ears of Mickey Mouse, are attracted to the negative chlorine atom, so they dissolve or tear apart the salt. Seawater is made up of 6 main ions, and then there are a bunch of very minor ions, but 99.8% of the dissolved inorganic material in seawater is just these 6 major ions. So it's important to know what these are. So chlorine, sodium, sulfate, magnesium, calcium, and potassium. You can see in the pie chart here, the breakdown by weight. So we have the largest percentage is chlorine, then sodium, and then smaller amounts, less than 10% for sulfate, for magnesium, and calcium and potassium. Chlorine is a much heavier ion than sodium, so in terms of weight, chlorine makes up a lot more of the composition of seawater, but in terms of number of atoms, chlorine and sodium are similar in the number of atoms. So this ratio between these 6 major ions is consistent regardless of what the salinity of the water is. So you can have very salty water like in the Dead Sea, or very fresh ocean water, so 32 grams per kilogram or something like that, and they will have the same proportions of these 6 major ions regardless of the salinity. So why is the ocean salty? Well, you've gone through what the scientific method is, so I'm going to propose a hypothesis here. The ocean is salty because rivers carry dissolved salts weathered from rocks on land into the ocean. Then when the water evaporates, it leaves the salts behind. So how would we test this hypothesis? Well, we'll compare the composition of seawater, so the different ions in seawater, with those found in rivers. So here's a graph of the 6 major ions plus 2 extra ones in seawater. So we have a large concentration of chlorine, sodium, sulfate, and then down to calcium, the K. And what do we see when we look at typical river water? Well, we do see 5 of the 6 major ions. So sodium, sulfate, magnesium, calcium, and potassium are all represented in river water. So it's possible for those salts to have come from rivers. You'll notice that there's no chlorine coming out of river water, but there's a huge amount of it in the ocean. So the concentrations in the river are obviously much lower than in the ocean, but that's not actually important in terms of can the rivers supply us with the ions we need. So the conclusion is that river input is very important, but it's not the whole story. It can't account for the chlorine we see in the ocean. So there's this concept of excess volatiles. So these are the components of seawater, most notably chlorine, that do not come from rivers. So chlorine comes from underwater volcanic activity or terrestrial volcanic activity, where the hydrochloric acid falls on the surface of the ocean. And a lot of other minor ions, remember the major ions make up 99.8% of the chemicals in salinity, but there are a bunch of minor ions, and a lot of these come from hydrothermal vents. So the figure on the right there shows a schematic of a hydrothermal vent. The details aren't super important, but we do see that seawater seeps into the seafloor, and then if it's heated up by getting close to the magma and undergoes chemical changes, transfers some ions to the rock around it and collects a bunch of other ones from the rock, so adds iron and other various chemicals to the hydrothermal vent fluid and then gets expelled back into the ocean. So is the ocean getting saltier? No. Over long periods, the ocean is in what's known as a steady state. So steady state is where the stuff going in equals the stuff going out. So there's no trend in the content of the ocean. There can be small fluctuations, but overall, there's no trend in what's going on. So in this figure here, you can see that there's a reservoir with 20 gigatons, let's say, of carbon, and then there's 2 inputs, each with 5 gigatons per year, and an output of 10 gigatons per year. So it's in steady state. The amount going in is equaling the amount coming out. This leads to the concept of a residence time, which is the average length of time that an element will spend in a reservoir, in our case, the ocean. And so the residence time is just the amount in the reservoir and the flux or flow in and out. So in terms of our simple example up above, we have a 20 gigaton reservoir and we have 10 gigatons per year going out of this reservoir. So the residence time of the reservoir is 2 years. So on average, every 2 years, all the fluid or the carbon or the quantity in this reservoir will be replaced. So it doesn't mean that each atom or molecule is in there for exactly 2 years. So an example would be residence time of students at UH. So, on average, residence time would be 4 years, but some people will do it in 2, will be at UH for 2 years, and some will be there for 6 years. So the average residence time does not necessarily represent the time that a particular molecule or element will be in the reservoir. So if we go back and look at our 6 major ions and their residence times, so you can see all 6 major ions have very long residence times. So chlorine has a residence time of 100 million years, sodium 68 million, and all the way down to calcium at 1 million years. But then we get to the 7th most common element in seawater, bicarbonate, and it has a residence time of about 1/10 of that, of 110,000 years. Bicarbonate is also biologically active, which means its concentrations vary depending on activity and depending on location. So all the major ions have a residence time that is much, much greater than the average stirring time of the ocean. So on average, the ocean, a molecule in the ocean takes about 1,000 years to move around the entire ocean basins. Just like with your coffee, when you pour milk in there, you stir it, the longer you stir it, the quicker the cream goes into solution. So same concept here, with thousands of stirring times, the major ions are well mixed. We have some other ions like aluminium and iron that have residence times of less than the stirring time of the ocean. These are important traces in that they don't last for an entire stirring cycle, so they give us more information about where they were released. Elements with long residence times, the 6 major ions, have a long time to accumulate in the ocean, so this is why their concentrations can be larger than we saw the rivers have. They undergo a large number of stirring cycles, so they'll be uniformly distributed, and they are conservative, and they maintain a ratio with the other long-term elements, long residence time of the elements. So this is why the 6 major ions always have the same ratio regardless of the salinity. Elements with short residence times are removed quickly in less than a stirring cycle. They are therefore not well mixed, and they don't have time to build up high concentrations. And as I mentioned, the short residence time elements are useful as traces of flow fields in the ocean.